We're going to demonstrate using Realis' software tool SABR, which is a shaft and bearing analysis tool. We're going to use this model to model an electric motorcycle transmission. We start with a model which has mainly been built. We will show some of the features for modelling shafts, gears and selecting bearings, and we're going to solve for the bearing type lives to look at the durability. Following that, we're going to export the results to generate some efficiency maps. We're then going to see if we can improve the efficiency of the gearbox. As you can see in SABR's three-dimensional view, the gearbox has already been built. It includes a motor rotor and then a primary gear which drives through an idler to an output gear shaft. This shaft would have a chain attached to drive the rear wheel. We don't have the chain explicitly modelled in here, but we can model, there are a number of ways you can model external loads within SABR. The chain load can be modelled as a torque dependent load where the vectors for a unit torque are multiplied by the actual torque passing through that shaft in each load case. The vectors are different for positive and negative torque, as the chain wrap around the small sprocket is not 180 degrees. Due to the short nature of the webinar, we are going to quickly see how to model a shaft from a 2D CAD profile which has been saved in DXF format. So if we look at the idler shaft here, it is currently just modelled as a cylinder. So if we look at that in section view, there is the cylindrical section. We can now select a DXF file, and it does not take long for us to match up some points that we create to that DXF profile. It's literally a question of clicking and dragging these points to match up with that profile, and as you can see, it only takes a few seconds to match this. If we want to, we can even type in the coordinates up here of each of these points, but in this case we can just click and drag those points, and if we need to, we can zoom in to make things a little bit more accurate with each of the positions of those points. We can also move lines so that there is a bore up the middle of the shaft, and we can just generate that very quickly. You'll notice that the two-dimensional view in the background has not changed. That's because we haven't yet committed the design changes that we've made in this profiling tool. We haven't committed those to the background. So we now commit those to the background, and there we have it. We have our shaft, and that only took a few seconds to model that, and in exactly the same way you can model all of the shafts in the gearbox. The next thing we will do is we will look to actually solve the gearbox for the bearing durability. So now we have our initial set of shafts and bearings modelled. We will have a look at the duty cycle. So the duty cycle has many operating points of the motor already set up. This includes the drive and regen directions, and the different torques and speeds correspond to the maximum power line from the motor, and they have been compressed from road load data and durability test data to give a number of hours at each operating condition. SABR's solver calculates the bearing lives for each operating condition according to ISO 16281, which takes into account the bearing clearances, any preloads, operating misalignments due to the shafts bending, and also the lubricant conditions, so the lubricant viscosity and cleanliness. And then the required life at each of these operating conditions is divided into the calculated life to give a damage figure. And these can be summed using the Palmgren minor theory to give an overall damage. 100% damage, for instance, equates to a 10% failure rate. Depending on how the duty cycle is derived will dictate the actual required damage limit. In this case, we will accept a damage limit of 80% as the duty is quite harsh with high levels of torque and power. The SABR solver will calculate the damage for all 6 bearings, so there are 3 shafts, each with 2 bearings, and it will take into account the shaft deflections from the applied gear forces at every operating condition. So we have about 15 different load cases across 3 different shafts, so we have to solve all of this matrix of solutions. The solver has been optimized to perform the non-linear Hertzian contact calculations faster than other solvers, and it also makes use of modern multi-core CPUs. So we will solve all of that, and as you can see, the solution is very, very quick, actually achieved in a number of milliseconds. We can immediately look at the bearing damage results, and if we look on this here, the color coding of the damage summary shows us that we have 2 bearings which are failing. They have gone over our 80% limit, which we can modify here. They've gone over our 80% limit, and in fact they've also gone over 100% limit, so they are shown straight away to be in the traffic light system to be red. So what we can do is we can look at the actual shaft loads themselves to try to understand why there might be a particular problem. And if we have a look at this, we can look at the forces on that shaft, and here we can see the forces. We can click on these arrows and that will show us the forces. So these are the 2 gear forces being applied at the gear teeth, and you can see that the vectors that these 2 forces are applying are going to be additive. Specifically in the negative y direction, those 2 vectors are going to be additive, and that is why the reaction forces that the bearings are having to react are very large. So instead of potentially just changing the bearings to be larger capacity, one thing we could do is potentially to change the actual position of the shafts. So if we go back to the 3-dimensional view and we look at the idler shaft itself, we can maybe see if we can move it to a different position. So instead of, at the moment, we have the alternative B position, with the same center distances though, there is another alternative position for that shaft, so we'll try alternative A. So it is now just dropped it down to the bottom here, and we can then perform the solution again. Again, it takes a few milliseconds to get that solution, and we can look to see what effect that has had on the bearing life. And lo and behold, without changing the bearings, without improving the bearing capacities, we have now reduced the damage on those bearings to acceptable levels. And why is this? Again, we can go and have a look at the actual forces that are being applied now on that shaft by the 2 forces from the gear teeth, and you can see here that to quite a large extent these 2 gear forces are now cancelling each other out. So that means that the reaction forces that the bearings are having to react are much lower, and that is why we have an improvement in our damage to less than our damage limit. So the next thing we can do is we can look to generating some efficiency maps, which is what we'll show next. Okay, so now we are going to replace the durability duty cycle that we have with load cases which cover all of the speeds and torques of the motor. So this can be used to determine the efficiency of the gearbox at each operating condition. This map can then be used in a system analysis, such as within our tool Ignite, to determine the range of the vehicle across drive cycles. We can generate the duty cycle across the speed and torque range. The duration is unimportant. The temperature here is set as a reference, but we can export results at multiple operating temperatures when we generate the maps. The operating points are generated in a geometric progression, as the efficiency is very non-linear at low torque and speed, but becomes much more linear in both the speed and torque axes at higher motor powers. We've created 225 operating points, so we'll replace the durability duty cycle with those. And now if we go to the shaft loads, then obviously we can see the solver hasn't been run yet, so we'll solve that. And again, you can see that the solver still generates the results in less than a second. The efficiencies are calculated according to two ISO standards, ISO 15312 for bearings and ISO 14179 for gears. These take into account the speed-related losses due to oil churning and the torque-related losses due to friction. The results in SABR are in a column format, which is not very convenient to look at. So what we can do is we can export them to our tool RMap. We can now determine the temperatures that we would like to export out to. The reference temperature is 80, so if we want a temperature of 20 degrees C, we need to put -60 to refer to that reference of 80, -40, -20, 0 and 20. So we have 5 operating temperatures now running from 20 degrees C up to 100 degrees C. We will export that map out, save it, and now if we open up RMap, we can have a look at the file in RMap. So the map here, we can see the efficiencies. They've been cut at 0.87 as the minimum and 0.97 as the maximum. And at the moment, we're looking at 20 degrees C, and we can see here that down at the low torque end, but the high speed end, there is basically a lot of oil churning. So the efficiency is very low at that point. But as we increase the temperature, the viscosity of the oil comes down, and so this churning loss becomes less and less, and we can see at 100 degrees C it's even less. So we're still churning oil down at this end, which is why the efficiency is below 0.87, but it's a much smaller area. So we can now go and look at the SABR model itself and see how we can improve the efficiency of the gearbox with some design changes, re-export the results and have a look at the comparison of the two efficiency maps. So now we have generated the efficiency map, we will look at the gear pairs to see if they can be made any more efficient. If we look at the input idler gear pair, we can see that there is a high relative slide velocity ratio, i.e. it's not close to unity. This means that as the gear exits the mesh here, there is higher relative sliding between the gear pairs than when it enters the mesh. And this can be seen from the distance from the pitch point here to the end of active profile is much larger than the distance from the pitch point to the start of active profile. So that is why we have a significant difference in the relative sliding. So we can actually use SABR's parameter sweep function to look at changing some of the inputs, such as module, pressure angle and profile shift, to try and achieve a better efficiency whilst maintaining the safety factors. The parameter sweep which we have run runs about 1900 design variants. This took about 2 minutes on this laptop to run, and we can then filter the results. The first filter we have applied with just the safety factors has produced 363 results. But we will now also filter the relative slide velocity ratio to be close to unity and put a minimum filter on the transverse contact ratio of 1.4. If we apply those filters, we now have 16 results which have passed those filters. We can now sort those in terms of the efficiency. So if we click on the efficiency column, we can actually sort so that we have the maximum efficiency design. So we will click on that and we will save that to another file. We will quickly design the output pair as well and then import them both into SABR. We know that the durability is okay from the gear perspective because we have applied those filters, so we know that that is okay, but we need to check the bearings have not been significantly affected by the gear design change. So that is the next thing that we will do when we import these designs back into SABR. Okay, so now we have saved that file. What we can do before we import it back into SABR is we can just have a look at that particular gear pair and see how it compares to the original file that we had, the original design that we had. And you can see here the relative slide velocity ratio is very close to unity, and if we have a look at the profiles here, we can see that where the end of active profile is, the distance from the pitch point to the end of active profile is very similar to the distance from the pitch point to the start of active profile. And that is why we end up with a relative slide velocity ratio that is very close to unity. So we will now import those designs back into SABR, and it is a very quick process for us to be able to do that. We do the same for the output pair, and now we can run that again. All of the results are out of date because of all the force vectors have obviously changed, and we can just perform the solution again. Similarly, it takes only a few milliseconds to run, and we can just check to make sure that there is not a major change to the bearing damage results, which there is not. So the next thing we're going to do is we're going to look at possibly changing some of the bearings to see if we can improve the efficiency of the actual bearings within the model. So there are two drawn cup needle roller bearings on the idler shaft. We can note the damage is fairly low for these bearings, less than 40%. So we will look to see if we can replace these with ball bearings. So if we go onto the two-dimensional view and select the idler shaft, and I'll just select that shaft on its own, and we will look if we can replace these with ball bearings, because ball bearings are typically more efficient than roller bearings as they have point contacts rather than line contacts, so they have lower friction. So SABR has online catalogues of bearings from manufacturers such as SKF, Timken and Koyo, which can be selected. Alternatively, details can be entered in from catalogues and saved to a user database and shared between users. The bearing catalogues come with filters. These filters can select on bearing bore, bearing outer diameter, bearing width, dynamic and static load capacity, and limiting speed. These filters can be very useful in narrowing down the selection to relevant bearings. In this case, the dynamic load rating of the drawn cup needles is 8,400 newtons, and as we know that the bearing damage is less than 40% and our target is 80%, we can use a lower dynamic load rating, or DLR, as the minimum limit in our filter. So we will change to a ball bearing, deep groove ball bearing. We will put in a maximum width that we already have, which was 12 millimeters, and we will actually use 7,000 newtons as our minimum limit. And what I'm going to do is I'm going to select, there are many bearings that we can select that have dynamic load ratings above 7,000, but I'm just going to select the first one in the catalogue here, as it is narrower than our existing bearings. So we need to do exactly the same for the other drawn cup, and we will change that to a deep groove ball. We will show the catalogue. Again, put in the width limit and the minimum capacity of 7,000 newtons. And again, we will select the same bearing, and that is now attached. We do need to change the constraints on these because they will not both be constraining the axial forces. There are no axial forces because it's spur gears, but still we need to just make sure that these are constrained correctly. And as you can imagine, the left hand ball bearing will stop the shaft from moving to the left, and the right hand ball bearing will be stopping the shaft from moving to the right, with casing trapping those two sides. So now all we need to do is rerun. We have changed the bearings, so we just need to rerun the model, and it is again it is a matter of milliseconds to get the results, and then we can just check on the bearing durability. And as can be seen, the damage has gone up slightly from the drawn cup designs, but it is still below our 80% limit. So these bearings are acceptable. And then the next thing that we will do is we will generate our efficiency duty cycle to run the efficiency map, and we can compare that then to the original efficiency maps that we got with the original gears and with the drawn cup needle roller bearings. Okay, so now we can do exactly as we did before and generate some efficiency maps. So if we go back to our duty cycle tab, and we will generate, we will replace the durability duty cycle that we have with our efficiency map duty cycle. So exactly the same number of points at exactly the same places as we had in our original map, 225 points. We will just replace all of those points there, the durability duty cycle with our efficiency duty cycle. Obviously now the solver hasn't been run, so we need to solve again. And again, it should take, yes, it's taken less than a second for us to generate all of those points. Again, we can have a look at the efficiency, but there's not a great deal of point here. So we will export all of those out to another efficiency map at exactly the same temperature points, so -60, -40, -20, 0 and 20 to cover the range of 20 degrees C up to 100 degrees C. We'll export those maps out, and we can now have a look at the two maps and compare them. So this is the new efficiency map that we have from our design, where we have all we have done is we have modified the gear design and replaced a couple of bearings. So there is no other substantive change. We haven't changed the lubricant conditions or anything like that at all. We've just changed the gear design and replaced a couple of the bearings. If we now compare this, this is at the 20 degrees C point. We can now compare to the original map. And you can see here, also at 20 degrees C, we can see that the large area of high efficiency has actually expanded. It was only up here before and is expanded all the way down to here. And the second colour here has expanded all the way down to this point here, which is much further than it is up here. So we have improved the efficiency quite significantly across a lot of the operating range. If we now just check and see what happens at 100 degrees C. We can compare between the two again, and again you can see that we have improved matters for a lot of the operating range. We have improved the efficiency, and all we have done is changed the gear design and replaced a couple of bearings. That has not cost us anything in terms of the design. We haven't had to do anything to any of the lubricant conditions. We have just replaced one gear design with another and replaced a couple of the bearings with more efficient bearings. We have the same durability as we had before, and a significantly improved efficiency, which should make a noticeable improvement to the range for our electric vehicle. So in summary, we have shown that with SABR you can model shafts very quickly and easily, you can select bearings from the online catalogue, and you can design the gears. The gears can be designed using our parameter sweep function, which means that you can target efficient gears whilst they are also durable. And following that, you can then export out the results to efficiency maps to compare designs for both gear design and bearing design to give you as efficient a transmission as possible. And these results can then be exported as efficiencies or losses that can be exported to a system tool such as Ignite. And that can then run through the drive cycle simulation, and using the efficiencies that will change during the drive cycle with temperature, then it can calculate the energy losses through the drive cycle and give you your range prediction.